Hello everyone. Welcome back to this lecture series on Design of RCC Structures. This is lecture 9 and today we are going to analyze rectangular reinforced concrete sections using the limit state method. So in the previous lectures, we discussed the concept of limit states and even we discussed the stress strain behavior of concrete as well as steel and the stress block parameters. In this lecture, we will apply all those concepts to solve numerical problems on rectangular beams and determine their ultimate moment of resistance. Now let us move to numerical problem number 1. So here a rectangular beam of size 350 mm by 700 mm is reinforced with 2 bars of 25 mm diameter and 2 bars of 20 mm diameter, which is being provided at an effective depth of 650 mm. The grade of materials being given as M25 grade concrete and Fe415 grade steel. So we are asked to determine the moment of resistance. So this is a typical flexural analysis problem in limit state method. So here the beam size is given, the reinforcement is already provided, so hence we are not designing the steel. We are only checking how moment of resistance can resist the loadings. Let us go with the given data. The width of the section is given as B 350 mm. Overall depth of the section is given as capital D 700 mm. Effective depth of the section small d is given as 650 mm. So now why this effective depth is important is, remember concrete resists compression whereas steel resists tension and the lever arm depends on the effective depth. So that is why all flexural calculations use only small d and not the overall depth. So here the steel provided are 2 numbers of 25 mm bars and 2 numbers of 20 mm bars. So using which we can calculate the area of the steel, which comes as 1510 mm square. Now for solving for the moment of resistance, the typical step which will be following is calculate the actual depth of neutral axis and check with the maximum depth of neutral axis or the limiting value. Then we can define whether the section is an under reinforced or over reinforced. Based on that, the moment of resistance can be computed. Now let us start with the XU by D, that is the actual depth of neutral axis factor. So which has been taken from Annexure G 1.1a of IS 456-2000, in which the formula has been given as XU by D is equal to 0.87 Fy AST divided by 0.36 FCK BD, wherein Fy and FCK are the characteristic strength of steel as well as concrete. AST is the area of the steel provided in the tension zone. B is the width of the section and small d represents the effective depth of the section. Since all the values are known, just substitute that values, we can get the value of XU by D as 0.266. Now for Fe415 grade steel, the XU max by D can be taken from the table which is available in section 38.1, in which for Fe415 grade steel, the XU max by D ratio can be taken as 0.48. So using this limiter, that is XU max by D, we compare the actual neutral axis depth and with the maximum allowable neutral axis depth. So here in this case, XU by D is less than XU max by D. Hence, the section is under reinforced. So why under reinforced is preferred in all the cases is, here the steel yields first, in which the failure will be ductile, which gives warning before collapse and hence safe and desirable. So for an under reinforced section, the moment of resistance is governed by steel yielding. So the general expression is given. This is the expanded one which is given in Annexure G 1.1b of IS 456. But the generalized equation is mu is equal to 0.87 Fy AST into D minus 0.42 XU that we derived in the conceptual cases of limit state design. So here 0.87 Fy represents the design stress in steel. AST is the amount of steel resisting the tension, where D minus 0.42 Xu is the lever arm. So this expression directly comes from the stress block assumptions, where forces and moment equilibriums were considered. So once you confirm the section is under reinforced, always use steel controlled moment equation. That is what has been given. Mu is equal to 0.87 FIASTD into 1 minus FIAST divided by FCK BD. Since all the values are known, just substitute that values, we can get the moment of resistance as 315.325 into 10 power 6 Newton mm, or otherwise 315.325 kilonewton meter. Now let us move to example number 2. Here again a rectangular beam has been given, in which the width of the beam is given as 300 mm. The area of the steel is given as 3600 mm square, which is being provided at an effective depth of 400 mm. So the grade of concrete is given as M20 and the grade of steel is given as Fe415. So we are asked to compute the ultimate flexural strength of the given section. So the key difference of this problem comparing to the previous example is, here steel area is directly given but not the number as well as the diameter of the bars. So here we must check whether the steel is excessive or insufficient. So let us rewrite the data given clearly. The width of the section is given 300 mm. Effective depth of this section is 400 mm. The characteristic strength of the concrete FCK is 20 megapascal, as well as the characteristic strength of the steel is 415 megapascal. The area of the steel provided is given as 3600 mm square. So again, similar to the previous problem, we should calculate the actual depth of neutral axis factor, and that should be compared with the maximum depth of neutral axis factor. Based on that, we can define whether the section is under reinforced or over reinforced, and finally the moment of resistance or the ultimate flexural strength of the section can be computed. So here the Xu by D, based on the given data, it's been calculated as 1.504. And again, similar to the previous problem, here also the grade of steel is given as Fe415. So for Fe415, the Xu max by D has been taken from the IS 456-2000 as 0.48. So now in this case, Xu by D is greater than Xu max by D. Therefore, the section is over reinforced. So what over reinforced section means is, here the steel does not yield first, but the concrete will crush first. Also, the failure is sudden and brittle, and hence it is not desirable. But we can calculate the moment of resistance based on the concrete capacity. So in general, we know for a over reinforced section, the moment of resistance will be governed by the concrete, and hence mu can be calculated using the generalized equation of 0.36 FCKB into XU max into D minus 0.42 XU max. So that expanded equation, which is being given in annexure G 1.1 C, in which the reduced formula based on the Xu max by D value is being taken as 0.138 FCK BD square. Here for over reinforced section, we never use steel stress directly because the concrete controls the failure. So the moment of resistance after substituting the values of FCK, the width of the section as well as the effective depth of the section, which is being calculated as 132.48 kilonewton meter. So let us summarize today's lecture. We analyzed rectangular RCC sections using a limit state method. So two numerical problems were discussed. We identified both the problems were classified as under reinforced section as well as over reinforced section. Different moment equations were applied to different cases, wherein section were classified is purely crucial before calculation itself. In the next lecture, we will extend this concept to design of singly reinforced rectangular beams. Thank you.